Hello, everyone. Today I will be presenting our paper entitled SpaIn-Net, which stands for Spatially Informed Stereophonic Music Source Separation, which has been a collaborative work between Dr. Minje and myself, Darius Petermann. So our main motivation with this project, pop music follows a relatively predictable mixing scheme, where each instrument in the stereophonic field holds a relatively known and distinct position. So in general, deep neural network implicitly absorb the spatial information that are generally conveyed by the input mixtures, for example, by means of stacking the two channels at the input stage, and that in order to optimize the separation process. As for existing spatial source separation systems that are making explicit use of spatial information, there are two routes. The first one is based on disjoint orthogonality among the sources in the TF domain that assumes that the sources in the spectrograms are poorly correlated. The second one are a system that we call instrument agnostic that performs separation solely based on the source's location. So our goal in this work is to come up with a system that harmonizes these two paths, a deep learning based supervised music source separation system that could potentially make effective use of spatial information as a conditioning mechanism. So informed deep neural network systems have been very effective in that path. For example, for music source separation, they make use of score information or pitch contour information in order to improve the separation process. So in this work, we claim that supervised music source separation could further benefit from some additional high-level spatial information in view of not only improving the separation process, but also providing an entry point towards user interaction. So once again, in this work, we start with the assumption that pop music specifically follows a somewhat consistent mixing schema, where all the musical instruments present in the musical mixture have a somewhat distinct location within the stereophonic field. So for example, we can make the assumption that the kick and vocals are generally to the center of the stereophonic field. And in this work, we call this information prior mixing knowledge. So this information can be provided potentially by the user towards improving the separation process. So roughly, this process would involve the following steps. So first of all, we're given a pop song that is following a typical mixing setting. The user has a rough estimate on the stereophonic position of the target instruments, for example, in this case, guitar and piano. And it's worth noting that this rough estimate can actually be rough and not exact. I'll tell you more about this in a little bit. Then the stereophonic position can be provided as an angular degree value, here represented as alpha. So for example, in this case, alpha is minus 30 degree for the guitar and plus 30 degree for the piano. Now we separate the sources using a supervised deep neural network. These two angular locations are fed to the system as auxiliary input along the stereo signal, which is the main input. And finally, at the network output stage, we get a better estimate on the target instruments thanks to these priors. So now, as for the baseline architecture, we use cross-on-mix, which has been very popular for music source separation task. Cross-on-mix works in the time frequency domain by taking first the STFT transform of the input time domain mixture. Each branch in this network, 1 through J, is meant to carry source-specific mask embeddings. One part of the novelty in this architecture is the fact that cross-on-mix introduces averaging operation throughout the architecture and allows for multiple sources to be considered together. So in contrast to its predecessor open-on-mix, here we perform cross-branch operation to get the most of all the sources altogether. After these averaging layer, each decoder outputs source-specific spectral magnitude soft mask. These soft masks will then be used towards predicting each source's magnitude spectrogram, and that by means of element-wise multiplication with the original input mixture. And finally, we recover the time domain sources by taking the inverse STFT. So our proposed method presents different conditioning mechanism, each depicting different ways of incorporating this user-provided spatial information into this cross-on mix system. So our spatial scalar alpha, which again expresses an angular value, goes from -45 to 45 degrees. And the reason for such range is that we follow a typical two-speaker stereo setup, where the speakers are placed symmetrically, 45 degrees angles and equidistant to the listener. So our panning range is essentially 90 degrees. Beside alpha, we also have our input spectrum mixture X. So our first method consists in concatenating alpha to both left and right channels of X. This would involve tiling alpha to the number of time step of our input spectrogram. So in this scenario, we could think of the contributive weight of alpha towards the resulting input as 1 over the number of frequency bin of the spectrogram. Our second approach is more straightforward. We essentially sum alpha to X. So this just means that for each time step and frequency bin, we add alpha to the initial magnitude value. And finally, our third approach consists in taking the positional encoding of alpha and summing its resulting positional encoding map to the input spectrogram. So positional encoding was originally proposed as a part of the transformer model paper cited below, in order to give the model some sense of order to each word about its position in the sentence. So this approach differs from our previous summing approach, as in this case, each value along the frequency dimension is varying. So in summary, at this time, alpha is not constant along the frequency dimension of the spectrum, but its frequency is varying. And that frequency will be based off the original alpha value. So for example, the frequency variation of the positional map at -1 and 1 degree will be very close together. While the same at minus and plus 45 degree will be substantially different as they depict the two extreme of our range, basically. So for the experimental design, we used a SLAC data set consisting of MIDI synthesized mixtures with varying numbers of sources. So we defined two instrument setting use cases. The first one we call 4S, so involves totally different instruments. And the second one, 4SJ, involves two different instruments of the same nature, guitar 1 and guitar 2, with obviously very similar timbral characteristic. So this one is a difficult task for a supervised deep neural network, as especially if it doesn't involve any spatial information. So we added this use case to potentially show the merits of our spatially informed method by showcasing how well the network deals with two sources containing very similar timbral characteristic, yet having different stereophonic properties. So during the data generation process, we randomly sample alpha for each of these sources from a uniform distribution, again, between -45 and 45 degrees. And optionally, we mimic a training scenario where the user would provide an inaccurate alpha value. So we add noise to the ground truth alpha in this case. And once again, we pick this noise out of a uniform distribution ranging from -8 to 8. And finally, we mix these four sources together using the constant power panning law depicted below. So for the experimental results, we're now seeing the result for the first use case, which involves 4 different distinct instruments. As a reminder, D0 is our baseline, our clean angle scalar concatenation D1 cat alpha, D1 cat overline alpha depict noisy angle, and finally, we have our DF add, which depicts a clean positional encoding summation. So we first note that our method display a clear advantage over the baseline with, we can see an increase of about 1.5 decibel SDR. Overall, the positional encoding conditioning outperforms both clean and noisy concatenation method. And one key thing to note is that the system trained on the noisy angle outperforms the clean angle counterpart for both noisy and clean alpha evaluation. And that's very important to note because it means that this system, which is robust to error and accommodate for user imprecise estimates, results in a system that is as successful as the one with the oracle spatial information. So now for the second use case involving guitar 1 and guitar 2, we see that once again, in comparison to the baseline, there's a clear merit coming from our spatially informed approaches. So we see a pretty notable increase of about 2 decibel SDR on average. We also see that this time the concatenation conditioning methods are outperforming the positional encoding one. And one other thing to note is that the noisy and clean training and evaluation observation that we made in the previous use case still stands for this use case. And finally, we note that guitar 1 is the source that is the most affected by the noisy angle training. So this means that the source separation for guitar 1 and guitar 2 actually relied greatly on the spatial information and much more than the other sources due to their timbral similarity. So now to wrap up, I will play a few audio examples for you, denoting how our best performing model, D1 concatenation trained on oracle angular values, sounds against the plain cross-on mixed baseline. So as a start, I will play the input mixture. And now ground truth for the guitar 1. Ground truth for the guitar 2. And now onto the baseline predictions for guitar 1. So we can hear that guitar 2 is actually predicted as guitar 1 in this case. Now guitar 2 for the baseline. So we can hear that basically guitar 2 and guitar 1 are predicted as being guitar 2. In this case, guitar 1 is totally lost. And now our proposed model for guitar 1. So guitar 1 is actually successfully retrieved in this case, thanks to the spatial information. And this is guitar 2. Thank you very much. You can find the source code of our model at the following, as well as additional audio examples also at the following. Thank you.